Okay, let's start then. So this week, the topic will be recurrent neural networks and transformers. These are both architectures for basically both architectures of neural networks. So they're not specific to recommendation systems, but we'll mainly talk about them, mainly talk about like the subset of topics that are useful for recommendation systems. And both build on top of what we already talked about. So I think in previous weeks you saw what like a basic feed forward neural network is. By that I just mean a fully connected neural network where you have a hidden layer or multiple hidden layers, and every input basically has a weight that connects it to every hidden cell, and then it's the same thing from that hidden layer to the next hidden layer, where you have weights wherever possible, basically. And then you combine multiple of these linear layers with activation functions in between to sort of model a more complicated function. Yeah. So table of contents, we'll go through a few topics today. First is tokenization. This is how you pre-process text for the architectures we're going to talk about later. And then RNNs, recurrent neural networks, LSTMs, we'll talk more when we get there. Then we'll talk about the attention mechanism. And from there, we'll talk about transformers and also the pre-training of transformers. Yeah, both RNN and transformers have their roots in natural language processing. This is not to say that they can only be used for natural language processing, but they're good at processing sequential data, which language is a sort of sequential data. And there are many types of tasks you can do with sequential data. For example, sentiment analysis, if say your system wants to look at a review and determine a score for that review, you want to quantify how much a user likes an item based on a textual description they give, or you want to say classify text. Yes, I'll put a copy of the slides on Piazza immediately after lecture. Or say if you want to classify text, right? This might be, you might want to do this from like a content-based recommendation side. Say you have a bunch of news articles and you want to know like what to recommend to who. And in that case, it'll be helpful to have an automated way to classify text into categories. And also there are more complicated tasks. So sentiment analysis and classification both fall under sort of the classification category, where your model takes a bunch of text and then spits out one answer, spits out one classification. But there are more complicated tasks where you might want to have it spit out another sequence of data. So for example, text summarization, or if you're talking about like translation, you're also trying to map a sequence to another sequence. Yeah, and our naive approach for this sort of problem is from what if we're just using what we have before, is just to stack a few fully connected layers on top of it. Of course, at some point, this neural network will be expressive enough to actually so that it can like actually learn the problem well in theory, but in practice there are several problems. One is that yeah, actually, so just to make this picture a bit more clear, the inputs aren't necessarily numbers. So they start off as words, right? And then we convert them to numbers. And each number can have one hot vector that represents it. And then basically the process where we turn the words into a vector or some other quantified form that we can actually feed into the network, that process is tokenization. And we'll talk about it in a bit. And yeah, so this sort of naive approach, the main problem is that it has way too many parameters. Also, it doesn't scale well with the length of your sentence. So you can imagine in our fully connected networks, you have a fixed size of inputs. So usually you have a few distinct features that you put into the network as input. But in this case, your sentence can be arbitrarily long, right? And you don't want to, like one way you can get around this is just to have your network have like a max sentence length that it can handle. But like, first of all, you'll eventually run into some sentence that's longer, or if you actually if that max sentence length is really long, then you'll have way too many parameters because you're fully connected, right? You'll also have to scale the hidden layers to account for longer sentences because like if you have a fixed size for the hidden layers and long sentences, it'll get to some point where your network just isn't expressive enough for the long sentences. Yeah. So let's talk about the pre-processing step first before we get into the more advanced architectures. So tokenization is the process of turning text into data that your model can interpret. And there are several ways to do this. Two of the most simple ways, I guess, are just tokenizing it word by word, which means every word will be mapped to a specific integer. And then once your network gets that integer, it can learn some sort of embedding for it. Actually, usually you'll have an embedding layer first that turns that integer into a one-hot vector or a more complicated vector, and then or a dense embedding vector, and then that vector is fed into the network. The other way to do this is character by character. It's the same idea, just every character is mapped to an integer, and then your network gets an embedding for that integer and then processes it as a vector. And there's a trade-off here where if you want to make the tokens more fine-grained, like if you want to do it character by character, you'll have a smaller vocabulary size because there are less characters than there are combinations of them. But your sequences will all be very long. The other advantage of doing character by character is that your model can effectively learn anything, but that can also be a drawback because that means it has to learn the spellings instead of just seeing like a specific spelling as a different word. It would have to learn that, okay, this spelling of these characters is means this word and the other spelling means another word. And so there's a trade-off between vocabulary size and sequence length. And like on the other hand, if you use word by word, you'll have a massive vocabulary. Remember that you need one embedding per word. So if you have like tens of thousands of words in your vocabulary, that means tens of thousands of embeddings. And each of those will be a vector of a non-significant size, of a not insignificant size. So your vocabulary size does eventually increase your number of parameters by quite a bit. And one way to get around this trade-off, or at least find at least find like a sweet spot in the trade-off, is using byte pair tokenization. What this means is you'll start with a base vocabulary. This can be characters, or you can choose bytes to do this. But to make it more, to make it easier to understand, we'll just use characters as the base vocabulary here. So the first thing you'll do is you'll find the most common combination of characters. So in this case, the first thing that you start off finding is the pair of characters that appears most often, and then you'll combine them into this meta character. So if you find that UN, this sequence occurs very common in your text, you'll just combine UN into another character and just say, okay, UN is now my meta character. And then you can repeat this process. You can keep combining the most frequent combination of meta characters until you reach a desired vocabulary size, right? So in this process, you're always finding new words for your vocabulary, but the way you find these new words is you're finding, okay, which combination is most common, and which means it'll be worth remembering. So if a particular combination like UN happens very commonly in your data set, then you're basically deciding to do, say, okay, it's common enough, so we'll dedicate another embedding to it and make it a different character, right? So on the right, you can see how this process might deal with a word like unrelated. So RE is a pretty common combination in English. So it might combine those two first, and then AT, and then ED. At this point, you're still combining individual characters, but you realize that actually these meta characters can also be combined, right? You see AT and ED as two separate meta characters eventually gets combined into ATED as well. And if you keep repeating this process, eventually everything will be combined together. But the reason you want to stop is because your vocabulary size keeps increasing. You just want to stop at the point where you think you've reached the appropriate size of vocabulary. Yeah, and then once you've figured out what your vocabulary is, you still have to represent it as vectors. And there are two ways to do this. One is to use sparse embeddings. So you'll turn every integer label for the number. So each character will be mapped to an integer, right? And then that integer will have a corresponding one-hot vector. Or you can do what's called a dense embedding, which means instead of having the one-hot vector, you'll just have a vector represent that token. And these will be learned vectors. But in practice, usually you can just implement it as a sparse embedding. And once this token goes into your network as a one-hot vector, your later layers can sort of learn the dense structure on top of it. Yeah, so once again, our naive approach with the fully connected layers, the main problem is that it doesn't handle variable size input, and it has a large number of parameters, or a very small number anyway. Like the number of parameters doesn't change with your input, so it could be either way too large or it's just not expressive enough. Now, one way to improve this is to look at how we did how we did computer vision with neural networks. We used these convolutional layers that took advantage of spatial locality in images to learn more efficiently. So instead of connecting every single hidden layer neuron with every single input, we're saying, okay, we only want to look at the local features first. And then we like keep combining local features until we have like a global view of the entire input. So here we're taking advantage of like an inductive bias in the data. It's because as humans, we determine that in image data, local dependencies are more important, because like we see that images, like interpreting images, is largely dependent on recognizing texture and patterns locally first, and then like combining those small features like lines and corners into larger features like shapes, and then eventually into more abstract concepts like objects, right? So is there a similar structure we can exploit for language? Well, there is a recurrent structure to language, right? When we read text, we read from left to right, and we remember something as we go. As we consume each word in the text, we remember something that not only adds to our memory of the text, it can also affect how we consume the next word, right? So that's why we choose the architecture of a recurrent neural network. So it also reads the text from left to right, token by token, and it'll maintain a context of what we have so far. Now, the reason this is called recurrent, is that it's actually the same set of weights when you consume the same token. So like you see a long network on the right here, right, on the right of the equal sign. So it looks like your network gets larger as you have more input, but that's actually not the case. It's the same network that's handling every token that's being fed in. So it consumes the token, changes its state, and then consumes another token, changes state, and just moves right in the text. So to take a closer look at the RNN cell, it's essentially a very small, it's just one fully connected layer, but we stack it in a recurrent way so it can handle longer sequences of input. So here, if you look into the single cell, it has like an input xt, which is basically the teeth token in your input or whatever sequence you have as input. And then that input will get projected by a fully connected layer, this W matrix, WH, XH, XT. what W does is it just does a projection to a different number of dimensions. And that's the same thing that that a fully connected layer would do. And then you combine this X with what's called a hidden state. So at first you'll have an arbitrary hidden state that you can initialize it somehow. And then that hidden state will get passed into the first cell, and the hidden state gets combined with your input, both after projection. It gets combined into your input, and then that produces the output of this cell. And the output also gets sent to the next cell. So this thing is called the information that's being output and passed to the next cell. That's called the hidden state in this case. It'll basically remember new information from the token that you just consumed, and it'll affect how you will output. It'll affect how you it'll affect what you output in future cells as well. Right. So input comes in, updates the hidden state. The hidden state passes to the next cell. The next cell takes the next token, changes its hidden state, and then passes it along to the next cell. And at every cell, you have the option to also output some function of the hidden state. In this case, it is just a projection of the hidden state. So once again, another fully connected layer on top of that. So as you can see, in this case, you only have 3 matrices that do the projections. It's the same matrix here. It's the same set of 3 matrices for every cell that you repeat. So it doesn't actually have more parameters as you have more input. It's the same network applied recurrently on the input. Yeah, and of course you can always stack more layers. In this case, you can stack the RNNs in parallel. So the output of your RNN cells at every time step can be interpreted as another sequence for the next layer of RNNs. And that's what you see in this diagram here. So the outputs at each time step from the lower recurrent neural network gets fed to the top recurrent neural network, and it similarly also outputs something at each time step. Now, there are many ways to structure these RNNs. As you can see, it gives an output every time step, but sometimes you don't actually need that. You just want one output from reading over the entire text. So that's why you have these different structures. So the one that we'll look at primarily here is many-to-one, which many just means it takes in many tokens from the text as input and outputs one vector, one embedding of the text. And then that vector, you can use it for classification, sentiment analysis, whatever. All right. But the point here is that no matter how long your text is, you're only interested in perhaps one feature, one particular feature of the text. And you also, and for other tasks like machine translation, you'll have many-to-many. So it could be the case that every time steps output matters, or actually in this diagram, what happens is your RNN reads over the entire text and encodes it. And then after this encoding, it starts spitting out output at every time step. Yeah, so this is what's called an encoder-decoder structure, but we won't go into this too much in this class because our concern is mostly with classification tasks. Now, one problem with RNNs is called vanishing gradients. And how this problem happens is often, like especially for many-to-one tasks, where we want the RNN to read over the entire input and then produce an output on which we do the classification, the only gradient coming in will be through that final output, right? Because the gradient comes from the loss function, and then that flows back down the network through the history of applying this RNN. Yeah, so when you get to the earlier tokens, it might be the case that your gradient vanishes, which just means it has just passed through too many weights that the partial derivative has vanished. So this doesn't necessarily mean that the gradient becomes 0, but the weights will update very slowly for the earlier tokens that it won't be able to trade effectively there. So basically it's not learning much from the earlier tokens, and the classification ends up being mostly dependent on the final tokens. Yeah. Are there any questions at this point? Oh, sorry, I didn't see the text. The chat. Yes, you can also use a CNN for sequence processing. You can use like a 1D CNN to process the text sequence. That has worked in some cases, I think, but it's more common to use, at least it was more common to use RNNs and LSTMs. Now it's more common to use transformers. What is the goal we want to accomplish with the inputs? So the input will be a sequence of text, and we want to produce a classification of some sort. So like I said before, one sort of classification you might do is sentiment analysis. You want to determine if a review is positive or negative, or you might want to like classify the text. Or you might want to classify a textual article into some classes. So hidden state is passed from previous token to next token. It's passed from the previous cell to the next cell. How do we understand that? How do we understand what each hidden state output from the RNN represents intuitively? I think of it as a summarization of the text that has read so far, because that's the only information. The hidden state is the only information that the RNN keeps after reading all the text so far. So if it eventually uses that information to make the classification, then it has to have some sort of encoding or summarization of all the text that it has read before, right? And it makes sense why you update that at every token, because you've read a new word and you want to change what you remember about the text sequence so far. Yeah, and then the way to get around this vanishing gradient problem is to use what's called long short-term memory cells, LSTM in short. And the main contribution that these things have is that they introduce this long-range memory that doesn't get bottlenecked by every cell you add in front of it. So let's look more closely at this diagram of the cell. It looks pretty complicated at first, but once we break it down, it's just, there are three main functions that it does. So instead of having just one hidden state, it has two types of hidden states. There's a cell state, which is the long-term memory, and there's the hidden state, which is the short-term memory. Then within each cell, when you take in another input token, it does three things. So the first thing is called the forget gate. It's the leftmost red box you see here. So your network, your cell takes in, your cell takes in the input token and the hidden state from the last cell and determines a vector called ft. So this ft will, your cell state, okay, let's just think about the cell state and hidden state are as the long-term and short-term memory. Because it's recurrent, let's just assume they represent those things when we start the analysis. And in the end, you'll see that they do represent those things. It does make sense that they represent those things. So your long-term memory comes in and your short-term memory comes in. You produce this F vector that's dependent on your new token and your short-term memory. And you multiply your long-term memory by that token, by that F vector you produce. And what that does is it allows you to forget certain information in the long-term memory. Like you might see a new token and decide, okay, some information is no longer relevant from the long-term memory. And the way you'll forget that is just by maybe multiplying a vector where it's 0 at a certain entry. And then your long-term memory basically loses that information. And that's what this first red box does. And then the second gate is, I don't think it's called the remember gate, but it basically does, what it does is it incorporates new information into the long-term memory. So it also looks at the new token and the short-term memory, the hidden state, and it produces this I vector. And this I vector gets yeah, let's just leave it aside for now. It also it does a similar thing with, once again, takes the input token, takes the hidden state, and produces this C vector. This is basically the thing that it decides to add to the long-term memory. And you see here, the way you update the long-term memory, the cell state, is you add the previous state of the cell state multiplied by F. So this is the cell state after forgetting what you decided to forget, and then plus the modification that was produced by this gate. Right, so the cell state comes in, and then depending on what the hidden state and the input token is, you decide to forget something from that state, and you also decide to add something to that state. And at the output, what happens is this output doesn't actually affect the cell state anymore. At this point, we've already done with everything we want to do with the long-term memory, and we're just our final steps are just to decide what to output at this cell and how to modify the short-term memory. And what happens there is the output is just a function of the hidden state and the token, and the hidden state gets updated as some function of the cell state. So eventually your hidden state, the short-term memory, becomes a function of the long-term memory that's immediately combined with the token in the next cell, and then and that turns into the output in that cell, and then also the modifications to the long-term memory that you eventually decide on. All right, so to go over this once again, your cell state and hidden state both come in. The hidden state and your input together decide what to forget from the cell state and what to add to the cell state. And then your hidden state and your input produce the output while your cell state gets passed to the next recurrent cell. Your hidden state is then replaced with a function of the cell state. Now, there's also a way for it to sort of keep what it had in the last, like your hidden state doesn't necessarily get refreshed at every recurrent cell, because it can inject some information into the cell state, which is immediately sent back into the hidden state, right? So it's able to add to the cell state, and then the cell state produces this hidden state. So you don't necessarily refresh the hidden state, but there is there's a less direct dependency here. And then the hidden state gets past the next cell and keeps on performing the role of this short-term memory that's very frequently replaced by some function of the long-term memory. Yeah, this gets around vanishing gradients, because if you think about how the gradient flows, there's one easy path for it to flow backwards, which is just the cell state. The cell state does have things added to it and multiplied into it along the way, but it never gets cut off quite like the hidden state, right? So the gradient's able to flow pretty far back into the history, and this allows the LSTM to learn effectively on long sequences. It also allows it to capture long-range dependencies better, because one signal can stay in the cell state for a long time without getting cut off. And if you remember from convolutional neural networks, this is very much like residual connections, where we make a connection between the neurons that skips layers that allows it to retain information across these long-range dependencies. One modification to these RNNs is to make it bidirectional. So sometimes you don't just want context from the earlier words to produce the output at that token. You also want the context from the right. In that case, you'll just have two RNNs, one that reads the text from the left, another that reads it from the right. And then at each token, you concatenate their outputs and then act on that to produce whatever embedding you need. And then the new question that in the chat, if we're classifying some text, would we be using the last H or all the intermediate HI? Usually you can just use the last H, but you can also concatenate all the H outputs and then use that to make the classification. But if you're just using classification, then yes, the last H is good enough. And this is actually a bit of an open-ended question, because like in the encoder decoder architectures we saw before, what we used to do is encode the entire text. So have your RNN read the entire text and then output one hidden state. So you get the last H out. And then you have another RNN take that H and decode it into a bunch of tokens. But the problem there is that there's a bottleneck of information where the encoder is only allowed to pass one H vector into the decoder. So that might not do well on long sequences. So what we did later is basically to allow the decoder to see all the intermediate HI from the encoder. And that actually sort of leads me to the next topic. Actually, are there any questions about LSTMs? And okay, so that leads me to my next topic, which is attention. So let's say our RNN encoder produces outputs for each token, and we want a classifier to classify the text using these encodings. So this is related to the question, because here we're assuming we want to look at all the output HI. We're not just looking at the last one, but you have to have a way of combining these intermediate hidden states. So one mechanism for this is attention, right? So you want to decide on weights. You want to somehow produce weights for each token, which represent how much you want to attend to them, and then take away the sum of all the tokens as your as the vector that you want to do the classification on. Yeah, so let's say your model determines that so this A function here just represents some sort of function, some attention function, basically. So it'll look at two positions and decide how much. It'll look at one position in your input and decide how much it wants to attend to that location, and that will be the attention weight for that token. And in the end, to produce the combined vector, you'll take a weighted sum of all the input vectors. Now, this mechanism looks pretty simple at first, but what's powerful about it is that people figured out that you can actually just replace the entire encoder with this sort of mechanism. And you can stack many layers of attention, of course, with other layers in between, but it's a powerful mechanism for so-called contextualizing text information. And that leads us to transformers, which are a architecture that basically has as its core a bunch of attention layers. And these are the state-of-the-art in NLP right now. So most of the large models like BERT, GPT-3 you hear about are based on transformers. I'll release this, I'll send a link to the slides on Piazza together with the assignment and quiz and stuff after the lecture. Yeah, so in this paper called Attention is All You Need, this is the paper where where we were first introduced to transformers. What they did was they replaced this encoder structure. So our previous encoder was an RNN, right? They replaced this entirely with attention. So this means that you're no longer processing the text in an autoregressive way. So you're not consuming one token at a time and then spitting out one token at a time. Instead, you're processing everything in parallel. And this allows every token to combine information from all the other tokens. And we often use a word called contextualize to describe this process, because the way attention, at least the way self-attention works, is that every word is able to attend to other words in the sentence and combine information from those words to give itself context. And you can repeat this many times, right? So you can get context from a bunch of other words. So each word is able to get context from a bunch of other words in one round. And then at the next round, it can further contextualize itself with the contextualized versions of other words. Yeah, so, but we still have the problem of determining the attention score. So how do we know how much a word would like to attend to another word? And the way we do this is with these things called queries, keys, and values. So for each input token, it'll be projected into a query, a key, and a value. And the way these things work, first of all, the projection is you can do it with a fully connected layer, which just means multiplying by a certain matrix. And here we represent it as WQ for query, WK for key, WV for value. And then you have, for each token, you have a query vector, a key vector, and a value vector. And then you want to look at a specific token and you want to see how it will contextualize itself, right? So now you have, say you're looking at word one, you want to contextualize word one. It'll have a query. So what happens first is it'll take its own query and take the dot product of that query with every single key from all the other words, right? So that's why it's named query and key, because basically the word has a query where it asks for information from other tokens. And then the other tokens have a key that sort of represents what information I have, right? So the dot product just represents how well of a match the query and the key is. So it's a match between what that token, intuitively you can think of as a match score between what that token wants to find and what information other tokens have. So you get this dot product between the query and every single key for the other, with every other token's key. And that will basically be your attention weight. Of course, you'll have to do some extra math to make sure the magnitude is right. So what they did in their paper is they scaled it down by the square root of the dimension of these vectors. And they took the softmax of it. So if you remember, softmax, it interprets the scores as a probability distribution. So like one obvious thing that it does, it normalizes so that they add up to 1. And that sort of makes sense because you want all the vectors to be about the same magnitude. You don't want them to like double in magnitude when you add two different vectors together. That's why you'll like make sure that the weights you have add up to 1. Yeah, and those will be your attention scores. Okay, the dot product between the query and the key gives you the attention score. Yeah. Yeah, okay, you get the attention score and then the contextualized version of word one will be the weighted sum of all the tokens in your input that are weighed by the attention score of word one on those words. Yeah, in this diagram, what happens is, so the input produces a query, a key, and a value. Of course, the input two also produces a query, but here we're only focused on how the first word gets attention. So it produces a query, and then for each other word in the input, you'll take a dot product between the query and their key. So get a dot product score here, and the output at position 1 will basically be this score multiplied by this value plus this score multiplied by this value plus this score multiplied by this value. So it's the weighted sum by the attention weights of the values of each token. And here's a animation that makes it a bit more visual. So of course you're still only looking at how the word dog how attention is applied to this word dog. You'll have to repeat this process for every word in the sequence. Yeah, so dog has a query. It gets dot producted with the key of every other word. You get these scores. You take the softmax, and then you take the weighted sums to get the output embeddings. So here you can see the Y's on the right are for each of the 3 words. So what you see on the bottom animation is actually the process repeated for every word. And for the final word, you can see that these weights actually correspond to the softmax. So that is the word that is shown on top here. So the intuition is that, as I said, the word produces a query for what sort of information it wants to contextualize itself. And then it just combines values from other tokens to give itself context, right? And the reason I can say these things as if the weights actually have this sort of magical structure to it is because we're assuming that we'll train it later, right? So we structure the weights in a certain way such that the only way to make use of them is to use them as the sort of attention mechanism. And so when we actually optimize it, we expect it to learn some sort of behavior that's similar to what our structure guides it to do. Of course, it is not strictly faithful. What these models actually learn is not strictly faithful to what we expect them to learn, but oftentimes we see that they do similar things. For example, in this animation, you can see what words these words attend to. So on the left, the gray word is the word that's attending to other words, and on the right, the color of the word means how much that word is being attended to. And you can ignore this CLS and SEP for now. Those are special tokens in the BERT model that we'll talk about later. So you see that, for example, the word "the" it attends to the entire phrase. The rabbit quickly stopped. The rabbit quickly hopped. That kind of makes sense because this "the" is referring to the object represented by that entire phrase. And also rabbit pretty much attends to the same phrase. And for the other words, you can see, and then "the" attends to the phrase about the turtle. And I think "slowly" attends particularly to crawled. And that also makes sense because it's like an adjective describing the word crawl, right? Yeah, and so yes, softmax gets applied to the vector scores to normalize them. And that just means making sure that the scores add up to 1. The multi-head attention is not super complicated once you understand self-attention. It just means you have different sets of these projection matrices, so different ways to produce the queries, keys, and values. And that will just mean you have several copies of self-attention running in parallel. That allows the model to attend to tokens in different ways. So maybe one head, like each copy of the self-attention there is just one head. And so each head might have a different mechanism for attending to things. Yeah, that just increases the expressivity of the model. And in the end, you'll take the outputs from each head, concatenate them, and then project down back to the original size, right? So because like when you concatenate the vectors, it gets longer, but you still want the same sized vectors for each token. So you just use the matrix to project down. Yeah, and that is the main component of transformers, multi-head attention. The actual architecture involves some other layers, but most of them you might already be familiar with, right? So here is the architecture from the original transformer paper. Their task, they use this model for text modeling, I think. So that's the reason for different input and output component. But you can see like the basic component is you apply multi-head attention to the sequence of tokens, and then you also have a residual connection. This line that goes around the multi-head attention is the residual connection. That just means after you do, so you retain an original copy of the sequence of tokens and you add that to the one after attention. Then you have a feed forward layer that's just a fully connected layer. You also have residual connection around that, and that gives you one chunk in the encoder. There are some of these other components, but we won't go too deeply into them. So like basically this positional encoding thing, the reason for this is that you realize so far in our architecture, there's no notion of like input order, right? If you shuffle the sentence in the same way for each sentence, so if you reverse the sentence, if you reversed every sentence that the model saw, it'll handle it the same way because our model, every word is able to attend to every other word. So there's no actual ordering to them. That's why sometimes we want to give it information about which position the token is on by giving it this positional encoding. And then for the last topic of today, we'll discuss pre-training. This is the way we usually train transformers because, as you saw before, they have a lot of parameters and there's a very complicated structure in them that's hard to train with if you don't have enough data. There's also generally they require a bit more care to tune and train than, like, say, a CNN. So you might we won't talk about this in detail here, but something that's often done is called a learning rate warm-up. So you'll have a scheduled learning rate instead of a fixed learning rate, like you usually would for like simpler models. And the reason for the warm-up learning rate is so that your model doesn't like learn some doesn't optimize itself into some like local minimum that's a recoverable form. Yeah. So pre-training, the problem we face here is that you might want to classify a very specific sort of text. So let's say you want to classify news articles into whether they're liberal or they're conservative. You probably don't have a lot of labeled data on this very specific task, right? You might have plenty of data just from some news article station, but if you think about it, that's probably not enough data to learn the language and the text simultaneously, right? Because what your model needs to do is not just learn domain-specific things about what it means for an article to be liberal, what it means to be conservative. It also has to learn the language first. And even if you think you have enough data to learn the task, your model is probably not going to understand language just from that amount of data. But there is plenty of text data out there. And so pre-training is our way of basically teaching the model the language first before teaching it the task. That's how I think about it intuitively. Yeah, so the solution to this problem is to pre-train on large corpus to learn general language features, and then use the trained model to fine-tune it on the downstream task. Now, of course, these are different tasks, so they require different sorts of outputs. So maybe your task is a classification, but obviously learning the language isn't just a classification task. So there will be a change in architecture in there. And well, that's what we're about to talk about. So BERT, this model is pretty famous. There's a lot of research around it. And so this was pre-trained on a large corpus, and people have been fine-tuning it pretty successfully to other downstream tasks, such as text classification and sentiment analysis. So it was pre-trained on 2 self-supervised tasks. This is very similar to the word embeddings we talked about before, where you have a task that doesn't really require labels, but requires some understanding of language to do well in. So the first task is word masking. So when so in the pre-training procedure, you have this BERT model, right? And then you have a bunch of text, unlabeled text. What you'll do is for every sentence, you'll randomly mask out some of the words. That just means replacing them with a mask token such that your model won't be able to see those words. And for the objective, for the task is to have the model predict what those masked word is. And you can imagine, in order to do that accurately, your model needs to have some understanding of language. It has to understand the context of the sentence to accurately predict the distribution of the word that's missing. Yeah, it's analogous to word2vec, but you have a much wider context. In word2vec, you're just trying to predict a single word with the 5 words to the left or to the right, and also with a very shallow architecture. But here, your context is the entire text sentence, and your model is much more expressive. So it's actually possible for it to learn entire sentence meanings as opposed to just word occurrence probabilities. Right, and then the other task is next sentence prediction. The point of this task is to have it learn more large scale information. So the task itself is the model is given 2 sentences, and it just has to predict whether the first sentence, whether sentence A comes before sentence B. Now, the other thing you realize about this task is that they're very noisy. Sometimes even if you gave a human 2 random sentences from a article, they might not be able to tell which one comes first, right? Because sometimes they can, sometimes it's very obvious, but in other times it'll be almost, there'll be no obvious order to them, right? And there's no obvious answer to that. But that's okay, because statistically, your model still does better the better it's able to distinguish the cases where it can actually give the right answer and where it cannot, right? So it's okay that your data is very noisy as long as your text, as long as your data set is huge. In this case, the data set is huge because you don't need any labels. You just need a text corpus, and you can get that from web scraping and stuff. There's quite a big amount of text on the internet. Yeah, and the way fine tuning works is, so you'll train BERT on these 2 tasks, right? It learns to predict masked words, it learns to predict next sentences. And then you'll have this architecture with a bunch of weights in them. And you assume that these weights at this point have learned something useful, have learned some useful features for the language. And the next step usually is to put some classification head on top of your BERT model. That means the classification head will take in the embeddings from BERT and then produce whatever classifications you want for your task. And that is, of course, uninitialized at first, and you'll just train that on top of BERT, right? And sometimes you would freeze the weights in BERT, which means when you when you fine tune BERT to the downstream tasks, in that case, you only want the classification head to change its weights, and you want to keep BERT the same way as it was after pre-training. And the other option is not freeze the weights and just have BERT tune its own weights as well as your classification head's weights. And that way it's able to basically get a very large head start on the task, on this, what's called a downstream task. That just means the more specific task you're performing. So like text classification, sentiment analysis, something like that, right? The pre-training just gives it a good head start to allow it to actually learn effectively on a text-based data set that's not necessarily large enough for it to learn the language itself. Yeah. Yes, this is essentially transfer learning. There are a lot of libraries that allow you to use transformers. Because this is so widely used, like, it's very common for people to just use BERT and fine tune it to some other task that requires natural language processing. So a lot of people have implemented these libraries. I think the main one that's being used now is the transformer library from Hugging Face. Like Hugging Face is like a company, I think, that maintains this library. And you can also get all the pre-trained BERT models from there, right? Because training BERT from scratch, most people probably don't have the compute to do that, but a lot of people do have the compute to do inference with BERT, right? So you can just use weights that have been trained by like the original authors. You can use those weights and then fine tune them to your downstream task, and that'll be affordable in terms of compute. Are there more questions? Okay, that was it for today. If are there more questions, not about this particular lecture, but about like course logistics? I'll release I'll release all the content for this week right after the lecture. So like quiz assignment and also the lecture slides. Oh, yeah, 3.3. That's just because I didn't delete the empty one. what would happen if we miss more than 2 lectures synchronously. I would have to check that